Now we will discuss some insertion operations that require RR rotation. So, consider the example like this. So, we have 2 at the root, then its left child is 1, right child is 3, then 3, right child is 4. So, assume this is the existing AVL tree. So, here you can observe, here for this one the balance factor is 0, for this node 3 the balance factor is -1, for 2 the balance factor is -1, for 1 the balance factor is 0. So, this is an AVL tree. Now, if we want to insert 5 here, suppose we want to insert 5. So, first compare 2 with 5. So, 5 is larger, so move to the right, then compare 3 with 5, 5 is larger, move to the right, then compare 4 with 5, 5 is larger, move to the right. Here the node 4 has no right subtree, so insert like this. So, 5 is inserted. So, it is similar to the binary search tree that we have earlier discussed. Now, when we insert 5, then find the balance factor after insertion. So, here for 5 it is 0, for node 4 it is -1, for node 3 it is -2, for it is 0. Now, for this one it is also -2. So, this node 3 has balance factor -2, this node 2 has also balance factor -2. Now, which node we have to select as the critical node? So, for this start from the newly inserted node, that is 5, move towards the root. So, 5 to 4, then to 3. So, 3 is the first node that have balance factor -2 in the path from newly inserted node to root. So, here in this example 3 is considered as the critical node. Now, from the node 3 move towards the newly inserted node. So, it is R or right. So, from 3 move to the right subtree, then we reach 4. So, from node 4 move to the right subtree, then we reach the newly inserted node. So, from the critical node, if we move towards the newly inserted node, we have to follow the path right or insert. I have written RR. Now, this RR, here we have to apply the RR rotation, that is like this. So, 3 is the critical node. So, pull this node 4 towards in this direction or in this direction towards its right, then let the gravity play his role. So, play its role. So, if gravity play its role, then this structure becomes 4 and here 5 is there and this 3 comes downward. So, if we pull this one, this 3 comes downward. So, 3 becomes here. Now, just join this one with the existing node or the remaining tree. So, if we consider the complete structure after insertion, then we can write like this. So, 2 is at the root, then 4, then 3, then 5, then 1. So, this is the AVL tree after inserting 5 and here it is a balanced one. Now, consider another example on this. Another simple example we will take. So, assume 12 with the root, then 18, then 20. Okay, so, this is the existing node, existing tree. Now, we want to insert 20 here. So, if we want to insert 20, the structure will be like this, then find the balance factor. So, the balance factor for 20 is 0, for 18 it is -1, for 12 it is -2. Now, from the critical node, that is 12, if we move towards the newly inserted node, that is 20, the path we follow is RR or right or right subtree or right child. Then, to perform RR rotation, here we need to perform RR rotation to balance the tree. So, for that pull this node in this direction or pull the right subtree of the critical node in this direction. Then if we pull 18 in this direction, due to the gravitational force or due to the gravity, this node 12 comes here, comes in this direction or falls in this direction. So the new structure will be like this. So 18, then 12, then 20. So if we insert 20 here, then RR rotation is applied because this tree becomes unbalanced, and after performing RR rotation, the new structure will be this. Then consider another example on this RR rotation. Okay. So now assume 14 is the root, 14 is the root node, then 12 is its left child, 20 is its right child, then 18 is left, 23. So this is the existing binary search tree. Now if we want to insert 44 to this existing binary search tree, so where 44 is inserted, so first compare 44 with the root 14, so 44 is higher, then move to the right, so compare 20 with 44, 44 is higher, move to the right, then compare 23 with 44, 44 is higher, move to the right. So for node 23, no right subtree is there, then add 44 here. Now after inserting 44, find the balance factor of each node. So for 44 it is 0, for node 23 it is -1, for 18 it is 0, so for node 20 it is -1, for 12 it is 0, for 14 it is -2. So now in this example 14 is the critical node, and from the critical node if we move towards the newly inserted node, the path is like R. So here we need to perform RR rotation, that means pull this node 20 towards its right or in this direction. Now if we pull 20 in this direction, then the node 14 comes here due to the gravitational force or due to the gravity, node 14 comes here. Now already 18 is here, so when node 14 comes here, it pushes 18 towards its right like this. So 18 comes here or follows or shifts in this direction. Okay. Now let us draw the new figure by pulling this one in this direction. So if we pull 20, so 20 will be the new root. So the new root becomes 20 here, then its right 23, 44 as it is, then its left becomes 14, then the left of 14 is 12. Now when 14 comes here, it shifts 18 towards its right, so 18 will be the right of 14. So this will be the new structure after we insert 44 to this existing tree. So this will be the new one after performing RR rotation. So this one, the above one is unbalanced due to the insertion of 44. So after applying RR rotation, we are going to get the structure like this. Now consider another example on this. So let us consider the root node is 2, then its left is 1, right is 4, then its right is 5, its left is 3. So like this. Now if we want to insert 6, to this existing AVL tree. So this is an AVL tree because each node is balanced one. So when we insert 6, so 6 is going to be inserted here to the right of 5 following the principle of binary search tree. So 6 is going to be inserted here. Now find the balance factor of each node after insertion. So the balance factor here it will be 0, here it will be -1, for node 3 it is 0, for node 4 it is -1, for node 1 it is 0, for node 2 it will be -2. So here you can observe minus 2 is the balance factor for node 2, and this node 2 is the critical node. So, from the critical node move towards the newly inserted node. So, if we move towards the newly inserted node, the path is RR. So, here you need to apply RR rotation. So, if we apply RR rotation and 2 is the critical node, so we have to pull the right subtree of the critical node to in this direction. That means we have to pull 4 in this direction. So, if we pull 4 in this direction, due to the gravity 2 comes downward and 2 becomes the left subtree of 4. Now, when 2 comes here, then it pushes 3 in this direction. So, 3 moves slightly right and it is attached to the right of 2. So, then draw the new structure. So, the new structure will be like this. So, if we push 4 in this direction, so 4 will be the new root here. So, 4, then right child of 4 is 5, then 6, no change here, then 2 falls here due to the gravity. So, the left child becomes 2, then 2's left is 1, no change. Now, when 2 falls here, it shifts 3 towards its right. So, 3 is going to be attached here. So, this will be the new structure after insertion of 6 to this AVL tree, and here RR rotation is applied. So, this is the new structure and here it is a balanced one. Now, consider another example on this. So, assume we have the root node 45, then its left is 36, its right is 63, its left is 54, its right is 72. So, this is an existing AVL tree. So, you can find all the balance factor are 0, 1 and -1. Now, if we want to insert 89 to this structure. So, if we insert 89, so 89 will be inserted here following the binary search tree. So, following the principle of binary search tree, 89 is going to be inserted to the right of 72. So, insert 89 here. So, when we insert 89, find the balance factor to check whether this tree becomes balanced or this tree is balanced, AVL tree is still balanced after insertion of 89, or it loses the property of AVLness. So, for that find the balance factor of each node. So, for 89 it is 0, for 72 it is -1, it is 0, it is -1, it is 0, it is -2. So, the balance factor of node 45 becomes -2, and due to this it is the critical node. So, from the critical node move towards the newly inserted node. So, path is RR. So, here you need to apply RR rotation and 45 is the critical node. So, to apply RR rotation, just pull the right subtree of the critical node in this direction. So, if we pull 63, that is the right subtree of the critical node 45 in this direction, then 45 comes here and 45 becomes the left subtree of 63. Now, when 45 comes here or falls here due to the gravitational force, you can assume. So, it is not actually in the computer's memory, no gravitational force is there. So, you can assume that due to the gravity the 45 comes here. Now, when 45 comes here, then it pushes 54 towards its right. So, the new structure will be like this. So, 63 becomes the new root and its left is 45, its left is 36, then it is 72, it is 89. Now, 54 becomes the right of 45. So, here it is 54. So, here you can observe this is the new structure when we insert 89 to the existing AVL tree. So, this one is the new AVL tree after insertion of 89 here in the above tree. So, this is all about RR rotation. So, the examples we have discussed that reflects or demonstrates RR rotation. Now, we will see some examples of insertion where LR rotation is required. So, consider we have a root and its value is 12, Now its left subtree is 4. So this AVL tree is a balanced one, or this tree is an AVL tree, because for this node, for the node 4 the balance factor is 0, for the node 12 the balance factor is 1. Now if we want to insert 8, so when we insert 8, so first compare 8 with 12, so 8 is smaller, so move to the left, then compare 4 with 8, so 8 is larger, then move to the right, so no right child of 4 is here in this example, so 8 is inserted in the right of 4. So when we insert 8, find the balance factor again after inserting 8. So here for 8 the balance factor is 0, for 4 the balance factor is -1, for 12 the balance factor is 2. So now here you can observe this node 12 becomes unbalanced, or here this will be the critical node. Now from the critical node, if we move towards the newly inserted node, so the path is like this, left then right, or in short we can write LR. So here the path is like L then R. So here we need to perform LR rotation to balance the tree. So for LR rotation, this is the critical node, so pull this node in this direction first, pull this node, that means the right child of the left child, or we can say jump 2 nodes from the critical node and pull that node. So if we pull 8 in this direction, due to the gravity 4 comes here like this, so the new structure becomes like this, so 12 with the root, then if we pull this one 8 in this direction, if we pull 8 in this direction, so let me draw here in a different color, so 8 and 4, so the structure of 8 4 is changed in this way. Now just join this 8 4 to the existing one, that is 12, so here it will be 8, here it will be 4. Now again here you can observe this one is also unbalanced, this is not balanced. Now pull the node 8, that means the previously where we have pulled 8 in this direction, now pull 8 in this direction. Now if we pull 8 in this direction, due to the gravity 12 comes here, so the structure is going to become like this, so 8 4 and 12. So like we have discussed earlier, in computer's memory no gravitational force is there. For easy understanding I am telling you with, or I am trying to explain with the gravitational force like that, but actually no gravitational force is there in computer's memory, or no gravity is required for balancing the AVL tree. So this is for easy understanding. So here you can observe in LR rotation 2 rotations required. So in LR rotation actually we need 2 rotations, one is RR, then another one is LL. That means we are pulling R in this direction, that is RR rotation, and again we are pulling 8 in this direction, that is LL rotation. So we can write like this, LR is equivalent to RR plus LL. So 2 rotations required, and here in which node we have to perform the rotation, or the in which node we are going to pull. So we are pulling the node that is right child of the left child or left subtree. So we pull this one, this node, or we can say like this, jump 2 nodes from the critical node and pull that node. So this is the basic of LR rotation. Now we will see some more examples on this. So consider a tree is like this. Suppose 10 is the root here, so we have the root 10, then its left child is 5, its right child is 12, then for 5 the left child is 2, its left child is 8, sorry, right child is 8, for 2 left child is 1, right child is 3, for 8 left child is 6, for 12 left child is 11, right child is 13. So now this is an given AVL tree, because this one is balanced, you can find the balance factor. So for balance factor we can write this one is, its balance factor is 0, it's 0, it's 0, it's 0, its balance factor 1, it's 0, 0, 0, 0, and its balance factor 1. So this is an AVL tree. Now we want to insert 7. So where to insert? So first compare 7 with the root 10. 7 is smaller, so come to the left subtree. So here we encounter 5, 7 is larger, so move to the right. Then here 8, so 7 is smaller, then move to the left. So we encounter 6, 7 is larger, so here we need to insert 7. So if we want to insert 7, we can insert here only. Now again, after inserting the new node 7, find the balance factor. So for 7 it will be, the balance factor will be 0, for 6 it is -1, for 8 it will be 2, for 0 it will be 1, for 1 it will be, for 10 it will be 2. So here in this picture you can find 2 nodes have balance factor 2. So for node 10 the balance factor is 2, for node 8 the balance factor is 2. Now which one will be the critical node? So to find the critical node, just move from the newly inserted node towards the root. So if we follow this path, then first we encounter 8. So 8 will be the critical node. So 8 will be the critical node in this example. Now from 8 move towards the newly inserted node. So if we move towards the newly inserted node from 8, so the path is like this, L and R. So here we have to apply LR rotation. So if we want to apply LR rotation, then we have to pull which node first? We have to pull 7, because move 2 nodes from the critical node. So if we move 2 nodes from the critical node, for LR rotation we have to move 2 nodes, and for LL and RR we have to move only 1 node. So we need to pull 7 in this direction. See, if we pull 7 here, then due to the gravity 6 comes here. So now the structure will be like this, 7, then its left child becomes 6 if we pull 7 in this direction. Now join this one, so here it becomes 7 and 6. So now join this one with the rest of the tree. So the rest of the tree is like this. So let me copy this one. Okay. So now these 7 and 6, so these are only updated. So 8, then its left child is 7, its left child is 6. So we are just, here you can observe the new structure of 7, 6 will be like this, and for 8 one left child is there. So simply we are putting the 7 and 6 to the left of 8. Now here you can observe this is not balanced one. For 8 the balance factor is 2. It is same as previous here. Here also 2. Now if we pull 7 in this direction, the balance factor also 2. So we have to apply one more rotation. So we have to pull 7 in this direction. So if we pull 7 in this direction, then 8 comes downward due to the gravity. So the new structure will become like this. So the new structure, 7 will become the root, its left is 6, its right is 8. So now merge this one or join this structure with the rest of the tree. That means to the right of 5 join this one. So let me copy this structure. So I have already copied, so we can, okay. So here you can observe, okay. So to the right of 5 just add this one, 7, 6, 8. So here we can right 7, its left is 6, it is 8. So now you can observe this one is a balanced one. So all the balance factor will be either 0, +1 or -1. Here you can update this one. So now the balance factor you can find for this, it will be 0, 0, 0, and for here also it will be 0, and for 10 1 2 3 1 2, so it will be 1. So here you can observe this one is the balanced one. So in LR rotation we have to perform two rotations, one is RR then LL. So we will take another example on this. So now consider we have an AVL tree like this, 45 with the root, then 36, then 63, then 27 its left, and 39 its right. So now if we want to find the balance factor, this is 0, this is 0, this is 0, this is 0, this is 1. So this is an AVL tree, all the balance factor are 1 or 0. Now if we want to insert 37 into this, so we want to insert 37 here, insert 37. So for this part compare 37 with the root. So 37 is smaller, move to the left. So we encounter 36, 37 is larger, move to the right. Then we encounter 39, 37 is smaller, so move to the left. So here we have to insert 37. Now after inserting 37, again find the balance factor. So here you can observe when we insert 37, then the balance factor of the nodes in the that falls in the path from 37 or the newly inserted node to the root are going to be updated. No other nodes balance factor will be updated. Like for 63 it will be 0, for 27 it will be 0, no change. Similarly you can see in the previous example, when we insert 7 here, the balance factor of the nodes following this path are going to be updated, and here the balance factor will be same as it was earlier. So when we insert a node, then the balance factor in the path, the balance factor of the nodes that fall in the path from the root to that node are going to be updated. So here for 37 the new balance factor will be 0, for 39 it will be 1, for 36 it will be -1, then for 45 it will be 2. So now here you can observe for node 45 the balance factor becomes 2, that is not allowed. So we have to perform some rotation to balance this tree, and here 45 is the critical node because its balance factor is 2 and this is the only node whose balance factor is 2. So from 45 move towards the newly inserted node. So we have to follow this path, this is first left then right. So we can write here we have to perform LR rotation, L and R. So if we want to perform LR rotation, then which node we have to pull towards right? This node. This node we have to pull towards right. Now if we pull this one towards right, then due to the gravity this 36 falls here. So I am drawing the partial structure. So 39 becomes the root, then 36 its left is 27. Then here you can observe when 36 falls here, it shifts 37 towards its right. So 37 is just attached here, and here you can observe no right subtree of 39 is there. So here no right subtree of 39 will be there. Now add this structure to the rest of the tree. So if we add this one to the rest of the tree, that means to the left of 45, because this part is changed and the rest of and this part is changed, so it is left of 45. So we have to join this one to the left of 45. That means the new structure will be like this. So 45 right 63, so 45 and its right 63, or let me use a different color for clear visibility. So 45 its right is 63, its left. So we have to join this one at the left of 45. So 39, 36. So 39, 39, then 36, then 27, 37, 27, 37. Now again we have to perform LL rotation on this node 39, because for LR rotation we have to execute two rotations, one is RR, another one is LL. Now pull this node 39 in this direction. So if we pull 39 in this direction, due to the gravity 45 comes here and becomes the right child of 39, and 39 becomes the new root if we pull this one. So now the new structure will be like this. So I am drawing here. So 39 becomes the root, and 36 here, 27, 37 here, 45 here, 63. So here you can find the balance factor of each node: 0, 0, 0, 0, -1, 0. So this is the AVL tree after applying LR rotation, or we can say after inserting this new node 37. Now we will take another example on this. So assume the root node is 9, its left is 4, its right is 11, its left is 2, its right is 6, its left is 1, its right is 3, its left is 5, its right is 8, for 11 its left is 10, its right is 12. So this is one existing AVL tree. So you can find the balance factor of each node. So the balance factor 0, 0, 0, 0 here. Now for this one is also 0, for this one also 0, for this one 0, 0, 0, this one 0. And here for node 9 it will be 1, 2, 3, 1, 2. So 3 minus 2, that is 1. Now we want to insert 7 into this existing AVL tree. So if we want to 7, so 7 first compare with 9, 7 is smaller, move to the left. Then we encounter 4, 7 is larger, so move to the right. So 6 we encounter. Now 7 is larger, move to the right. So we reach 8. So 7 is smaller, move to the left. So no left child is there for 8. So insert 7 here. So here you can observe we have inserted 7 to the left of 8. So now after insertion of 7, the balance factor will be updated. So find the new balance factor. So here it will be 0, here it will be 1, here it will be -1, for 0, sorry, for node 4 it will be also -1, for node 9 it will be 2. So when we insert 7, the balance factor of the nodes that fall in the path from the newly inserted node 7 to the root are going to be updated, and rest of the nodes are not going to be affected. So the balance factor of node this one, this one, this one is not going to be updated. Only the balance factor of the nodes that fall in the path from the root to the newly inserted node are going to be updated. So now here you can observe this balance factor of node 9 becomes 2. So that is not allowed. So 9 becomes the critical node because it is the only node in this tree whose balance factor is 2. So if we move towards the newly inserted node from the root, then we have to follow the path like this one, L and R. So here we have to perform LR rotation, and we have to pull which node? We have to pull this node 6 towards its right. We have to pull 6 towards its right. So when we pull 6 towards its right, then due to the gravity 4 comes downward, or 4 falls here to the left of 6. And when 4 falls to the left of 6, so here you can observe there is already a left child of 6, that is 5. So when 4 falls here, it shifts 5 towards its right. So the new structure after pulling 6 will be like this. I am drawing the partial structure now, then we can attach that partial structure to the existing one. So if we pull 6 here in this direction, so 6 becomes the root. So let me write here 6 becomes the root, then 4, then 2, it's 1 and 3. Now to the right 8 is there, then left of 8 is 7. Now 5, so 5 is shifted towards right. Whose right? Now 4's right. So in 4's right 5 will be there. So if we pull 6 in this direction, the new structure will be like this. Now attach this one to the existing. To the existing means here it is, the rest part are like this. So here 9, because these things are left of 9. So these part are left of 9. So we are updating these things and it is left of 9. So 9's left after this one. Then the rest part are like 9, then 11, then 10, then 12. So like this. So we have performed one rotation, but for LR we have to perform two rotations. One is RR, another one is LL. So again pull 6 in this direction towards its left. So if we pull 6 towards its left in this direction, then 9 falls here. So due to the gravity, and there is an existing right subtree. So when 9 falls here, then it shifts 8 towards its left. So the new structure will be like this. 6 will be the new root, or let me copy this one. Let me copy this part. Okay. So when we pull 6 in this direction, the 6 becomes the root. So 6 becomes the root, its left 4, then its right 5, 2, 1, 3. Then its right becomes this part, because 9 falls here and the rest part are unchanged, the right of 9. So 9 becomes the right of 6, 11, then 10, 12. Now when 9 falls here, it shifts 8 towards its left, the existing right subtree. So 8 becomes the left of 9. So it is 8, and we have one left subtree of 8, that will be remain as it is. So this will be the AVL tree after performing LR rotation. So I hope this is clear to everyone how we are executing the LR rotation. Now we will see another example on this, so that it will be more clear. So assume in the root we have 23 and its left is 18, right 44, then left is 12, then for 18 the right is 20, and here it is 4, it is 14, then for 44 its right is 52. So now you can find the balance factor of each node here in this example. So the balance factor of this one is 0, this one is -1, this one is 0, 0, 0, 0, this one is 1, so it is -1. So here the balance factor are 1, -1 and 0. So it is an AVL tree. Now we want to insert 16 here in this AVL tree. So if we want to insert 16, where 16 will be inserted? So first compare 16 with the root 23. 16 is smaller, so move to the left. We encounter 18. So 16 is smaller, move to the left. Then it is 12. So 16 is larger, move to the right. So it is 14. 16 is larger, move to the right. So 16 is going to be inserted here. Now after insertion of 16, the balance factor of the nodes that fall in the path from the newly inserted node to the root are going to be updated. So its balance factor is 0, its balance factor is -1, its balance factor is also -1, its balance factor becomes 1 2 3 -1, that is 2, its balance factor becomes 1 2 3 4 -2, so its balance factor becomes 2. Now we find two nodes and these are 23 and 18 whose balance factor becomes +2 and +2 here also. So whose balance factor is +2. Now which one will be the critical node? So the node we encounter first from the newly inserted node to the root. In the path from the newly inserted node to the root, the node that does not follow or does not have the balance factor 0, 1, -1, that node will be the critical node. So here node 18 will be the critical node. So node 18 will be the critical node. So move towards the newly inserted node from the critical node. So if we move towards 16 from 18, so the path is like left then right. So the path is left then right. So here we have to execute LR rotation. So when we need to perform LR rotation and 18 is the critical node, so pull 14 in this direction first, pull 14 in this direction. So if we pull 14 in this direction, what is going to happen? So let me copy this one. So if we pull 14 in this direction, then 12 falls here. So the structure will be like this: 14 comes here, then 12, then 16, then the left of 14 is 4. Now we want to add this structure to the rest part of the tree, or we want to join this one to the rest part of the tree. So the rest part of the tree is like this. So it is 23, then its left is 18, its right is 44, 52, then the right of 18 is 20, and this part is updated and the structure becomes like this. So we are going to add this one to the left of 18. So the left of 18 is like this: 14, then 16, here it is 12, here it is 4. So we have put this part to the left of 18. So here you can observe this part is nothing but this one. Now we have performed only one rotation, that is RR, but we have discussed that for LR we need to perform two rotations. One is RR, another one is LL. So again perform this LL rotation on node 14, that means pull 14 this one. So if we pull 14 in this direction, so 18 falls here, and when 18 falls here, it shifts 16 towards its left. So the new structure will be like this. So this part will be changed. So 14 will be the new root. So I am writing here 14 will be the new root. Then its left is 12, its left is 4, and its right is 18, it is 20, then 16 becomes the left of 18. Now this part needs to be attached to the rest of the tree, that means this part. So the rest of the tree we need to attach this part. So the rest of the tree is like this: 23 is the root, its right is 14, its right is 52, then its left is 18, 20. So these are updated. So just copy this one. So just copy this one and attach here. So here. Okay. So now this is the new structure after insertion of the node 16 to the AVL tree. So, this is the final balanced AVL tree after applying LR rotation. So, I hope this is clear. So, in LR we are performing two operations, one is RR, then we are performing LL rotation.